This is just a brief overview. The Canton Water Reclamation Facility is the project here, and the existing capacity of the plant's 39 MGD. Having a peak flow of 88, it's an existing tertiary plant doing nitrification. It's the largest project that the city has ever undertaken monetarily. It's probably not the largest construction project from the aspect of the facilities being built. Probably one of those was what's on this slide here, which is an aerial view of the plant, which was built in the 1970s. In the mid to late 1990s, there was a study done that included two phases of improvements. The first phase was upgrades of the course screens, increasing some unit processes to deal with some hydraulic issues in primary tanks and secondary tanks to eliminate diminished capacity due to regulations, and also some SCADA upgrades. Those facilities that were installed then are still used today. The second phase of those improvements that was looked at that time was improvements to the activated sludge process, which was determined to do something with at such time that they were increasing hydraulic capacity towards design flows, or if permit limits became more stringent. And at that time in the late 90s, it was decided to expand the plant from 33 to 39. That's why it's at the capacity it is today. And in 2008, the city was looking at increased nutrient removal. And probably the significance of bringing in the 1990 improvement is that had we proceeded with an improvement back then, membranes were not available. So in 2008, membranes was included in the equation. It was looked at as well as conventional activated sludge. And the difference in the cost was nearly $30 million to go with membranes versus building conventional activated sludge. And what the improvement did is it increased the capacity of the activated sludge tanks from 35 to 39 MGD, and it increased, or it eliminated the need for secondaries and tertiary, which would have had to been expanded as well. So what we have is a facility that's got influent screening. It's pumped up to an old preliminary treatment area where longitudinal grit and grease was installed with two-stage fine screening as part of this improvement. Primary tanks and secondary tanks were turned into phase 1 and phase 2 EQ. The MBRs were installed in the existing activated sludge basins, and tertiary and secondary was eliminated. These are the parameters being used for the design. The flows are very critical, both peaks, low, and average for membranes, because membranes are hydraulic limiting. And as you can see, the pollutant loadings are normal domestic loads. They're a little bit on the low end, but those are the loads that they've got there in Canton. The nutrients are phosphorus less than 1 and a total N of 8, which total nitrogen is on its way to Ohio. And the city felt that they wanted to address everything at one time. This is a schematic of the plant. We have of the activated sludge process only. We've got the influent coming into the anaerobic basin, which is used for BioP. From there it goes to anoxic, and then we have a swing anoxic, which is a tank that we can either run with air or as an anoxic basin to give us flexibility for changes in the pollutant loading over time. Then the pre-aeration basin and the MBR basin. We've got a 4Q recycle, traditional recycle coming from the MBRs up to ahead of the anoxic, and then we've got a 1Q recycle coming from the end of the anoxic to the anaerobic for BioP. In addressing this plant, there were a number of design aspects. With the preliminary planning, we were actually looking at putting membranes in for 110 MGD, but with further evaluation, we were able to reduce that down to 88 and using stage 1 and stage 2 EQ. As I mentioned, it's a BNR activated sludge. We looked at existing equipment such as blowers, and we were able to renovate 4 800 horsepower and 1 500 horsepower centrifugal blower for scour air. We did add new blowers for process air. We included a chemical system for BioP just on the chance that we weren't able to achieve it with the BioP. And we've got a carbon source in for total nitrogen because some testing that we did on the influent characteristic indicated that we might need some additional carbon source. The computer system that was installed in the 2000 is still being used, but we added to it an internal control loop, which is what's controlling the MBR system. And then the last thing is when you look at the overall plant plan, this is a plan of 7 MGD MBR trains. And one of the big issues with it is in the design was to make this plant what we might consider a small plant layout rather than one large facility. Each train is an individual plant of its own. It has all its internal pumps and recycles and so forth, rather than having a combined RAS or IR return and then having to be hydraulically split again. So what this does is it really simplifies the hydraulics and it keeps the equipment down to a size that's easier for the operators to deal with, both in weight and cost. Probably the easiest way for me to explain that is had we done a combined traditional RAS, we would have needed a pipe that was between 96 and 108 inch diameter. And what we have in each basin is basically a 30-inch or dual 30-inch pipes. So that's just one example of how doing each plant individually or each train individually as a plant, it helped reduce cost and keep things where it was simpler and in a small plant mentality. I'm going to turn it over to Kalpesh to continue.
Yeah. Thanks, Terry. To start with the factors involved during the installation or startup of this plant, we started facing, first issue was CIP makeup water quality. Since, as Terry told, that this was a retrofit job, so we had to maintain the continuous operation of the plant and treat the water, and at the same time build the parallel system within the conventional plant. So, and the problem was that the treated water coming from membrane tank and the conventional trains going to the same treated water tank, and from there we were using the clean water for CIP. So to solve that, we use the filters, but the problem with that was we need certain time frame to inject the chemical during the CIP, but due to filters in the picture, it was clogging and not allowing us to feed the water in particular time frame. So that was the first factor during the startup. The another was high solid loadings. So again, this is linked with the retrofit, because when you have 6 trains running and you shut down one train, you need to send that mixed liquor to other 5 trains. And that's where it's changing the mixed liquor to other trains. And at the parallelly was having some issues with the dewatering unit, which was causing the issues on higher solid loading to the plant, running with the existing train, as well as at that time we were running with a couple of other MBR trains. And the next one was the solid inventories. So we designed this plant on certain concentration of mixed liquor and running these with the different concentration coming in, and that's what making difference to the plant. And we'll explain in the further slides how exactly it was impacting the train. And then since again more emphasis is on retrofit, like limited train operations during the retrofit activity, because we need to continuously treat the water. Because of all these issues, the CIP frequency during the startup was every 13 days, and that was a concern for everybody, considering customer also. So we started work on in that direction, that how we can extend the filtration cycle, and these are some of the tools which we used to play with, so we can extend the filtration cycle for customer, and those are like mixed liquor concentration, suspended solid, water backwash, CIP chemical optimization, permeability set points, playing with it, chemical addition like MP50 and Scour Air to get the longer run time with the filtration. In terms of mixed liquor, so as I was speaking that this plant was designed with certain loads, and in reality the loads were a little less, but still maintaining the same mixed liquor which was designed for the plant. And because of that, it was creating sludge quality, filterability issue, and soluble COD. So we ran the BioWin tools, and based on that, we come up with a number saying that 9,000 is the number based on the current load which we need to maintain, and started maintaining on 9,000 mixed liquor in the tank. The another issue was that if we are already running at 12,000 mixed liquor or more than that, and peak event happen, and since during the peak event the recycle flow is half, so if we don't start wasting more sludge from the tank, it will drive or increase the mixed liquor in your membrane tank and stops or inhibit your capacity. So we suggested that if we have a peak event, we need to waste more sludge during that, so we don't accumulate more solids in the membrane tank. And we got positive numbers, and let me show you some correlation that how mixed liquor was helping to maintain certain soluble COD in the membrane tank. So here on the left-hand side, soluble COD, right-hand side, mixed liquor concentration, and bottom 4 lines shows the mixed liquor concentration. When it was below 9,000, the soluble COD number was, the top 2 lines are mixed liquor concentration, and when it was around 9,000, the soluble COD within the range. But you can see the bar, that's where the CIP was done, and the soluble COD number increased because we exposed microbes to the chemicals. So, and after that, when we raised the mixed liquor in train 1, the soluble COD further increased to the plant. So we explained customers saying that we need to maintain for this much load to 9,000 mixed liquor, and that's where we get the soluble COD in the system control, and that was helping us to maintain the stable permeability. The next tool we used was water backwash. So water backwash can knock off the accumulated solid on the surface of membrane. It's a useful tool if you have a reversible nature of fouling, and good options if the sludge is with the highly fouling in nature. So we conducted a couple of backwash without using chemical, and it gave positive results to the operations, and we could able to increase around 60% permeability during the operations. So the next table shows that on 25th Jan 1422 was before backwash number, and the first number 24.4 is when the permeate cycle was starting, the permeability was that, and at the end of the 9th minute, it was dropping to 18.2. So we did the water backwash, and then the after water backwash, the number was like permeability was 40 and dropping to 30. So it did improve. Just to see that how was the impact on next day. So on 26th, again we measured the permeability, and it was still high. So it did help, water backwash did help, and it depends on the water, your sludge quality. And the other tool which we used was using CIP chemical optimization. So lower chemical concentration will work depending on the nature of fouling and what target we are targeting for the recovery. So if we use less bleach, less cost, and less exposure to the bugs. And original plan in this case was 0.5% bleach, but we did try different chemical concentration, and we noticed that 0.25% and 0.4% was working for this project. And we introduced this to customer in terms of operating guideline. Normally, permeability we use as a monitoring tool for the plant, how easy water is permeating through the membrane. And we normally keep 10 GFD per PSI as our standard low permeability set point to shut down the plant, or before that we need to go for CIP. And when it comes to the warranty, it's a TMP number which matters. So since we were doing frequent CIP, just to extend the run of the filtration cycle or time frame, we reduced this number to 4 GFD per PSI, and it did help us to optimize the filtration run. And here are, with the impact of, combined impact of maintaining proper mixed liquor, suspended solids, backwash, proper chemical concentration for CIP, and lowering the number us to extend the filtration cycle for more than 25 days. So these these parameters were working for us at this project. Another one was chemical. So coagulant like alum and polymer like MP50 can be used temporarily to fix the sludge quality. And this material binds the soluble COD or the subcolloidal material in the system and make them big flocks. So when we use the MP50 to the plant, it improved the sludge filterability and reduced the soluble COD. In the trend, these are the live data when we added the MP50. If you can see here, the left-hand side is permeability numbers. So before adding MP50 to the plant, the permeability was dropping from 22 to 11, which means there was some issue with the sludge filterability or sludge quality, I would say. And after adding MP50 in a couple of hours, the permeability becomes stable. And that's where you can see that it was like between 20 and 17 within the cycle, and it was more like flat. So it improved the sludge filterability from 15 to 24 ml per 5 minutes of sample. So that's how we have seen the impact of MP50, but as I was saying, that this is a quick and temporary fix. This is not the permanent fix. Again, the trend showing that how MP50 helps to bring down the soluble COD number in the sludge. When the CIP was done, you can see that with the CIP, the soluble COD went up. So always when we do a CIP, your soluble COD of your mixed liquor goes up. And the red line shows that when we use MP50 to the plant, it drops the soluble COD, which means that the permeability at that time would be more stable, not going up or going down within the cycle. And the another tool we used was the air scar. On these trends, you can see that when the air scar number was 4781 SCFM, the permeability of that train was 6.9, and when we increased that to see the impact, the permeability did improve, and we saw around 30% of improvement on permeability during the plant operation. So that's how we use different tool to extend the CIP durations, so customer didn't need to do every other 13 days the CIP. And I would request Jesse to continue from here.
So Kalpesh also mentioned playing with permeability, and I just wanted to comment on that real quick. This is something that we tested and played with, knowing what we're doing and utilizing that as one of the tools to help improve and get away from cleaning so much. We knew that cleaning a lot and frequently was affecting our sludge quality. So by limiting that, and also we had drained the basins, inspected the membranes, we knew that they were not dewatering. So they weren't packed with sludge. We didn't really have that concern. We knew that there was something that could be removed from the membranes or treated in the biological process that we could address and give ourselves some room by reducing that permeability to 4. That way it allowed us to keep water going through the plant and clean less. So just wanted to comment on that. We're not giving you a license to run away with that permeability set point and set it to wherever you want. And then I'll get back to here. One more. Okay, so Terry introduced you to the size of the plant. It's a very big scope. It's a big project. I've been living up there and working on this thing for about 3 years, I think. But as you can see, this is just a screenshot of their overview screen. And there is a lot of data captured here. There's even more data beyond that if you click into some of these screens. This is just a snapshot. Now, it does get pretty easy to digest if you learn it. You learn one of those rows across the top there, and each train that follows is just repeated. So if you've learned one, you've learned them all. But it's still a lot of data. So once all 6 trains got online, there's so much information there that we needed to figure out how to capture and distill that down into a digestible format. So one of the approaches that we took here, excuse me, was we use a tool called Specific Energy. Some of you may have it. I don't think it's used that much out at our plants. But Specific Energy we made some adjustments to that, and we basically came up with a little report here. As you can see down in the lower right hand of the screen there, it's just a snapshot of basically, for example, at the top there, there's influent flow for each of the trains. We've got a 30-day flux profile. This big one here is just a quick snapshot. It shows you how much flow went through each train yesterday. The way that the bars are broken down there show you how much time did it spend in average daily flux or medium monthly flux or peak daily, just however they ran. There's a lot of information there that can be captured just by taking a quick glance at it. So if you're not colorblind like me, I might as well be looking at a bunch of holes punched through a piece of paper here. But I hear that there's amber and green, right? Is that true? If you can tell the difference, this is a tool that we used here to basically identify ranges where we wanted these aspects of operation to operate. And if it's within an acceptable range, then it's green. If it's not, then it's red. So we can get a lot from this just by looking at that really quickly. Just everything's where we want it to be. What's red, right? So this is just another approach that we use to distill all this data and information down to a digestible format. Other things that I don't really show you here, but things that we've built into those daily reports include plant influent flow, each train's operational flux, the mixed liquor ranges, turbidity, are the operational parameters good, like this one, and it also includes an alarm list for, I think, the last 7 days. So again, just the point was, we go in, we print this out every morning, and we've just got a report that says, here's most of the important stuff right here. And it's pretty easy to digest and call out what you might need to look further into. So in addition to that, so now we've kind of captured the information, and we may need to give recommendations or develop some guidelines for operating based on the information that we have. So we developed an operational guideline, and this is a living, breathing document. So we're constantly making revisions to this. If we go through and if we have an event or something, let's say we kind of have a lessons learned situation here, we try to take some parameters, as you can see here, and then make recommendations. So as you can see the SCOD up there, if it's less than 70, we consider it good. If it's higher than 70 but below 100, it's moderate, and it's pretty high SCOD if it's above 101. What those do, you don't really have the full guideline here, just kind of too much detail to break down and go over here in the conversation. But excuse me. So what we're doing is this is built-in guidelines. We're essentially, like we program a PLC, you have to define ranges, numbers. If I were a programmer, I'd have a better term for it. But we're basically defining the terms in which we can approach a scenario. So depending on where the SCOD is, we may want to consider that when we do a cleaning. Perhaps we don't want to go with a 0.4% bleach. We want to go with a 0.2. Things of that nature. So again, we try to capture all this and distill it down to a digestible format and basically program an automated response to things using an operational guideline. So we keep that accessible for the operators. It sits there right by the computer. Other things that we do in our operational guideline, just some rules of thumb. And I kind of caught Tate there a little bit earlier. I called him on the filterability question. We often say if filterability is above 10, then we're okay. But really, it's one aspect that may it may be one aspect of many that may be causing you an issue at your plant. So if your filterability is 12, it's still having an impact on the permeability of your plant. But at some point, you have to develop a rule of thumb. So again, these are rules of thumb. They don't always apply, but it just gives us some good working points to go with. Where was I here? So we got rules of thumbs, key limitations, just, don't operate your mixed liquor above 14,000 milligrams per liter. Some benchmark testing, suggested operating targets, and guidelines for when and how to CIP. So we've also included in there just some basic, here's what the plant's designed for, try to keep it in these ranges, things of that nature. And then the CIP, we have guidelines, like I mentioned, based on the results of other testing too. So once we have these recommendations, based on the last slide there, there's kind of a pre-programmed recommendation, but it may include a very detailed procedure. So again, in trying to collect all of this information and data and keep it in a digestible and usable format, there's a lot of procedures that we develop. Every time we want to do something different or something that isn't typical, then we develop a procedure for it. So we're just trying to capture all of this. I just slammed quite a few of them in here just for the sake of making the point. But as you can see, every one of these things, for example, we have a protocol for a bleach clean, just a typical bleach clean. We have a protocol for doing a backwash. And this all includes which valves do we go close by hand, which valves do we close manually from the CIP, what flow rates do we have to set these set points to. It's guided for each particular protocol, and this is how we capture that. So again, it's just, we've got a lot of information, a lot of optimization, and even some trial stuff too, and we have to capture all that in a format that we can go back to. But let's say it's successful, you want to be able to go back to that. So again, there's a lot of details here, and this is how we're trying to manage that and capture that. And we definitely recommend following these footsteps here. Even smaller plants can cause you a lot of trouble. So having a preset way to manage your issues and preset responses with detailed walkthroughs of what to do is really, really useful. Again, at this plant, it's operated on 3 different 8-hour shifts a day. So it's not like there's one operator who knows to do everything. The guy on shift A needs to be able to do the exact same procedure as the guy on shift B. So again, that's why capturing and documenting is really, really critical here. And we're just going to do some takeaways and wrap this up here. But for large and complicated plants, the circumstances can change frequently. You need to have a dynamic and operational guideline, or a dynamic operational guideline. It requires a consolidated summary report. So again, just digestible, quick, easy data and information. If the sludge quality is poor, a couple of things we learned here. If the sludge quality is poor, you could potentially just backwash your membranes. And again, this is another thing that we tested and proved that it was useful, as Cal Pesh went over that data. You can backwash with water, and what that did was it again, prolonged exposure of the sludge to bleach. So that now we could kind of get some recovery without affecting our sludge quality and kind of hurting ourselves in the process of helping ourselves. Optimizing chemical concentration for CIP. Again, we always dish out CIP recommendations with our new plants. However, they can be optimized. A little bit of testing can go a long way. We can optimize the MLSS in the system. Again, even though we have a range that you need, if your influent is different than the design parameters, then you may need to optimize your mixed liquor as well. Another thing we played with was increasing the air scour, and Cal Pesh went over that as well. More air scour seemed to help us with permeability and longer lasting without cleanings. And then consider using polymers like MPE50 to increase filterability. That MPE50, for me, when we got down to a permeability of 10 one day, that was the difference between me sweating this thing out all night and watching it for a couple of cycles and going home after that. Once we added the MPE50, we knew we'd be all right. So those are some things to consider for you, and that's going to wrap it up.
When you're backwashing the water, are you being trained in service and doing one set at a time, or doing the whole basin?
It was whole basin with the water.
The question was about backwashing with water and whether you did one train at a time or the whole, 1 unit at a time or the whole train.
Yes, yeah. we did the whole train instead of one unit at a time. Yes.
And how many trains did you have? I've forgotten now.
We have 6 trains. Each
Right.
train has 2 basins of MBRs.
8 rows and 53 SMUs.
Quite large then. Yes, sir.
What did y'all use for your calculation, like you set up your original MP50 dosage rate?
What did you use for the calculation of the MP350?
Formula you used to, say I put a gallon in, or
We jar
Yeah.
tested.
Yeah, the MP50 dosing procedure, you know, we have that same thing that we do everywhere. We do jar testing and figure out what's the optimized amount of MP50, compare that to the volume of the plant, and use that ratio to figure out how much MP50 needs to be at.
So what dose were you actually using of MP50 then? What dose was it, milligrams per litre, roughly?
It was 125 ppm.
125 milligrams per litre. Okay, right, interesting. Any other queries? Mark?
I got 2 things. We talk about SCOD, but we don't talk about the origin of it. Can you tell us what it is?
Okay, what's the origin of the COD? Soluble COD?
No, I can't.
No? Okay.
So you are asking about the original soluble COD?
So, we all sit in here and we can talk about mixed liquor concentrations, or we can talk about percentage of this, and concentration of that, but soluble COD isn't something that comes up in conversation too often.
Yeah, so in this case, we started monitoring soluble COD, and we did some benchmark testing that if we have soluble COD, let's say more than 70 ppm in the sludge, then where our permeability, how the plant is operating. And so based on the field observations and repeated soluble COD test, we could able to identify that if you keep your sludge soluble COD below 70, you have a healthy and good quality sludge, easy to filter through the membrane, and during that kind of operations, your filterability or permeability stays stable. It won't decrease within the cycle. If your permeability is decreasing within the cycle, which means that you have material in terms of soluble COD, it's an indirect measure of colloidal material or some material excreted by microbes or EPS, SMP kind of stuff. So we measure that with the help of soluble COD and try to keep within the limit by keeping proper mixed liquor and SRT to the plant.
Okay, well there we have to leave it. Sorry to cut in, but we're already running a little late. So thank you very much indeed, team.